Hello everyone. In this Universions episode, I would like to talk about advancing tensor theories, which is a work published in Symmetry Journal. What this theory says? A generic tensor T is simply the map between the generic combination of vectors V to the generic number set G written in this kind of formalism and symbolism. And this kind of symbolism has geometrical and topological interpretation using fractional derivatives, which are shown below. Here you can see a manifold M, and at some point P, there is the standard tangent manifold using standard derivatives, and the blue and green shows the fractional kind of tangent manifolds. Now, let's discuss a basic framework before advancing these tensor theories. Now, the standard tensor theories we can discuss about scalars, which is S, vector, V, matrix, M, and tensor T. You see that there is an example for a scalar, the number 1, which is one quantity, a vector has two quantities, a matrix has more than two quantities, and a tensor has multiple quantities that are described with indices 0, 0, 0 will give you an element of 1, while if the indices are other than 0, then you can have the element 0. Now note that the scalar quantity has non-index. The vector has one index, the matrices have two indices, and the tensors have more than two indices. And the important part is that there is an up and down index. Now, in the literature, there are multiple kinds of tensors being defined. And you see here, I can have two upper indices or two lower indices. What do you notice here? That each index has its own index. Therefore, new idea. I can create the index of the index of the index. And this can create a generic index, which is a mathematical calligraphy I is basically L of K through of J through I. What does this makes us? A generic tensor, T, which has L through I and alpha, beta through psi and omega. Therefore, we can build this new mathematical object, and this has huge amount of applications in mathematics, physics, engineering, and other parts of science. So let's discuss here the geometrical and topological interpretation of this kind of mathematical objects. You see here the standard interpretations are the following. A scalar can only describe a solution to a temperature problem. A vector can describe the solution of a directional problem. A matrix can describe the answer to a linear vector transformation, while a tensor a nonlinear vector transformation. A scalar can answer to the question, how much is the temperature in a room? For example, it can be negative 5 degrees, 5 degrees, or 25 degrees. A vector can answer to the question in which direction I should go and for how long. For example, you can go towards this direction in this angle for reference point for 5 kilometers. Now, a matrix will answer to the question how much I should transform linearly a set of vectors. For example, you can see here in this animation, I take a blue rectangle and this is transformed into a red rhombus. And to do that, I need some mathematics behind, and the main component is the matrix. And you see here, if I have described each edge of this rectangle by a blue vector, I can transform this vector using a matrix and I can create a new vector red. And this is done, this kind of transformation from blue to red by a matrix, M. Now, a tensor will answer to the question how much I should transform non-linearly now a set of vectors. For example, I start with a blue rectangle and now it doesn't become a linear shape, but it becomes like a non-linear new shape, which is this green new transformed shape. And to do that, I need to play with tensors. And you see here, there is a lot of mathematics happening behind in order to describe the transformation from the blue rectangle into the green tensor transformed shape. Now let's discuss about the advanced generic tensors. Now you see I can build an advanced generic tensor using T nu beta nu. And you see here, this can be transformed by the standard infinitesimal element dx nu, the partial derivative nu, and in the middle I need a fractional partial derivative with index beta and fractional derivative of 1 over 2. Now let's see an example. I can build this example by having at the 0, 0 component the number 1, at the 1, 1, 1 component the 0.5, and all other components can be 0. Now, this kind of objects have also geometrical and topological interpretation, which is basically a nonlinear and non-local transformation. And what does that mean? It does transform a vector non-linearly, but takes into account the non-local behavior of the property of the 2D space, which is described by this scalar field f(x) and y, which in our case, it's a simple function of x squared. And this models the property or potential of the 2D shape. And then I can build other kinds of transformation that take into account this kind of property. So why it is a non-local transformation? This is because the fractional derivative is defined using the Caputo approach, and this is basically the fractional derivative 1 over 2 of a function f of x is a factor with a gamma function 1 over 2, which is equal to square root of pi, of the integral from 0 to the x beta coordinate, and then a factor to the power of minus 1 over 2, which it's specific for this functional derivative, and then the standard derivative of the function, and then you integrate over all this space. Therefore, the fractional derivative takes into account all the domain of the x coordinate, accounting a non-local effect and a non-local transformation. So this is like remembering what is the properties of the full x domain in order to calculate the derivative, the fractional derivative. So let's see how this is done. I have a 2D shape, and then the generic transformation will answer to the question, how should I transform a set of vectors non-linearly and non-locally according to a property of 2D space. Let's fill this space with some property, the scalar field f of xy equal to x squared. And you see, it starts from the left from blue, and then as becomes bright, the value of the scalar field is increasing and becomes yellow, which the maximum value is 6.3. Now I take an object in the middle, which is with a blue color, as you see in the animation, and this is transformed into a red shape, which takes into account the property of this field. So in order to take into account correctly the property of this field, I need these new generic tensors, the advanced tensors that we described before. So I can have this new vector v, which takes into account the t nu beta nu vector with some field f of x and y equal to x squared. And this builds us this new kind of transformation, which are described by this new equation of t nu beta nu dx nu tensor product partial beta fractional 1 over 2 tensor product fractional mu. Now, I would like to mention that these advanced frameworks have several other applications in mathematics, physics, and engineering. And basically, you need tensors which are defined using fractional derivative, describe the transformation properties, then make geometrical and topological interpretations, and combine this generalized tensor theory with set theory and category theory, which are more advanced frameworks that can describe several other parts of science. Now, I would like to mention again that this work was published in Symmetry Journal in Advances in Algebraic Geometry and Topology special issue. The visualization of this work was done via macOS, Python, and Grok. I would like to give a big thank you to David Skinner, Spiros Karagiannis, and 4 anonymous reviewers who helped improve the study published in this journal. I would like also to thank every one of you that pay attention to this episode. And if you like the episode, like it and subscribe for more. Thank you for your attention. Happy mathing, everyone!